It's a great pleasure to be here again, and I've had a very stimulating and really enjoyable visit to Israel this time. And I thought in advance, what should I talk about? And I thought I would talk about catalytic chemistry. That's one of the main themes in my group today. And to give you both some fundamental idea of things one can do with what would seem to be one of the simplest reactive molecules, ethylene, and what we can learn. And you'll see some of this lecture spans a number of parts of the periodic table. Glad to have a periodic table there. And also impinges on some really fundamental sort of ideas in catalysis. So first of all, so that we're all on the same page, what do I mean by catalysis? And we've all seen We've all seen something like this in high school probably, but let's revisit a couple things that are so important that we really didn't learn in high school. The basic idea of what a catalyst does in terms of lowering the activation energy is kind of a no-brainer, but this is what's really fascinating. The sequence of steps that allows you to go from reactants to products in very intricate ways that can affect the selectivity of a reaction and the activity of the reaction. The other thing that's very general about catalysis is it's all around us. So homogeneous catalysts, there have been three sets of Nobel Prizes given in the last 2 decades for work in homogeneous catalysis. This is a close cousin, and as time goes on, these two fields have more and more in common. And then the other is heterogeneous catalytic chemistry, and this involves a separate solid phase. And if you think these kinds of things are just kind of trivial, academic exercises, catalysts and catalytic processes account for about 30% of the world's gross domestic product. If all of the Haber plants to make ammonia from nitrogen and hydrogen were turned off today, within about a year, 2 billion people, it's calculated, would die of starvation. So in terms of even public health issues, catalysis is very important. If you've seen pictures of Los Angeles in the 1970s compared to today, the automotive catalysis, the clean air, has had a dramatic effect on public health again. So catalysis pays off in many ways. And what I want to talk about today is the boundaries or the interface between this area and that area. Traditionally, heterogeneous catalysts have been a black box. How much can we really learn about how they work? And from what we learn, can we also impact homogeneous catalysis? And so the first part of this is a bit autobiographical. It had been known in the 70s and 80s, work mainly at DuPont at a Russian institute, that you could take some relatively innocuous, simple group 4 is over here, of organometallic molecules, put them on a surface, meaning just simply stir their solutions with, say, alumina, dihydroxide alumina, and their reactivity for certain transformations, such as olefin hydrogenation and polymerization, goes through the roof. So rate enhancements of 10 to the 6th or 10 to the 7th. And so as a naive young faculty member, I asked my heterogeneous catalytic colleagues, what do you think is happening? They said, it's a support effect. What's the big deal? It's a support effect. I said, well, wait a minute. What's going on? So part of the theme of this lecture today is to show you the advances in instrumentation and experiment, physical experiment, that allow us to see what's on the surface, and by doing that, to make a better catalyst. So with some solid state, high resolution NMR equipment, relatively primitive at that time, we could see that this molecule on the surface turned into something which we drew as having a methyl anion or an alkyl anion transferred to Lewis acid sites on the dehydroxylated alumina. I first proposed this remember this very well, at an ACS meeting, and this is a 14 electron D0 cation. And the response of the audience was sort of like, get this guy off the stage. This is absolute nonsense. But the counter to that is, what else is going to give you a 10 to the 7th-fold enhancement in, say, olefin hydrogenation activity, comparable to platinum metal catalysts? And so what we could see from the NMR was that this became much more electron deficient. These are solid-state C13 measurements. We put a paramagnetic probe here. We could see that this distance was greater than 5 angstroms. Now, in the response to the criticism is, we said, aha, I'm an organometallic chemist. I'm going to make a solution phase model for this structure that we can do X-ray diffraction on, we can characterize in all the elegant ways that organometallic chemists do that sort of thing. And as we decided how to do that, what happened was, at about the same time, Walter Kaminsky at the University of Hamburg took some trimethyl aluminum, which had been partially hydrolyzed and oxidized, a real mess of stuff. He threw it together with one of these metallocene, and the catalytic chemistry went through the roof again. And aha, we said, and at the same time, we were pursuing the idea of simulating the alumina surface with very strongly Lewis acidic sites with solution phase Lewis acids, and I'll talk about that. But the net result is, suddenly the petrochemical industry saw a completely different way to make polyolefins. We'll see why that's important in just a minute. And the picture that began to emerge is something like this. Here's this 14-electron D0 cation and a requisite, very, very special kind of weakly coordinating anion to stabilize it. The C13 NMR parameters of this looked identical to this, within 1 or 2 parts per million. So there's something really unusual and fascinating going on here. And the questions that we'd like to approach today, and this is a general lecture for general audiences, what is the nature? So if I put triflate there, I get no catalytic activity at all. If I put tetrafluoroborate there or hexafluorophosphate there, the cation simply abstracts fluoride. Wow, that is a hot electrophile. So what does this dotted line mean? Someone once said that dotted lines in chemistry really are an expression of our ignorance. Okay, so what does that mean? What if I poised 2 of these catalytic centers in close proximity? Might I see the kind of cooperativity that I see in, say, metalloenzymes, where they're 2 cooperating catalytic metal centers? And what is the nature of this kind of beast? Can I use it to do chemistry besides the very simple olefin polymerization? And so ultimately, what is the connection? Do we really have a valid model here for what's on the surface there? Can it be that heterogeneous catalysis really can teach us to make new homogeneous catalysts? And that's the second part of the question here. So where do we begin? We begin by telling you what I'm going to tell you. So we're first going to talk about organo group 4 D0 cations, as I've shown you here, and a little bit of understanding differences between surface and solid state catalysts. We're going to talk about cooperativity effects if we have 2 metals in proximity, and something that is going to surprise you. We're going to hydrogenate arenes with a D0 catalyst, not with a late transition metal catalyst, with a D0 14-electron catalyst. How the hell can that happen, you may wonder. And then just a very brief introduction. This all started because obviously this support effect was something more than just throwing something on an oxide surface. And now we're going to just take a brief sort of look at an oxo complex on activated carbon. Again, one of these mysterious supports, and this is probably where this was 10 years ago, but show you what we've learned already and why what we've learned makes it interesting to learn more. So that's the plan for the lecture. Polyolefins. So the annual US production in 2012 was about 110 billion pounds. And I can tell you, with the shale gas revolution in the United States, with light alkanes being incredibly abundant, it's going to get even hotter. And what can you do with polyolefins? Well, you can do everything from making automotive parts, medical implants, encapsulation of solar cells, all sorts of agricultural products. And the remarkable thing is, one catalyst, and what do I mean by a catalyst? Whoops, so there's an example of a catalyst there. One intricate molecule here, depending on the architecture, depending on the anion, I can feed it ethylene and I get some sort of oily, slippery stuff which I could use as a lubricant. Another catalyst could give me a crunchy powder, very high molecular weight, which I can use for this kind of application. Another one can give me incredibly strong, lightweight, flexible films. And the strength has to do with a lot of physics, a lot of how the chains entangle. So imagine if I have chains that have branches and the branches entangle, so there's the physics of pulling that entanglement apart translates into remarkable strength for remarkable light weights. So normally at this time in the lecture, I look for a trash can, because garbage bags, and I know that sounds trivial, but that's an example of some really interesting polymer physics to make something that strong. And all of this comes about because we've tailored the catalyst. And the problem with well, we'll say something about that in a minute, but so the motivation here is to understand new catalytic principles and also new polymer science. And we're going to focus for this audience mainly on this part. So you might say, we shouldn't be using polymers from hydrocarbons. We want to use polymers from sustainable sources, bio-derived polymers. So people have worried a lot about this, and this is an example of looking at the real numbers. And so this is an analysis of families of polymers that are available. This is a life cycle environmental impact axis, and this is adherence to green design principles. Now, we all know and like these bio-derived polymers, but in fact, you need a lot of water to grow the plants. You need fertilizer, you need tractors, you need a whole bunch of things which are quite demanding, especially if that land area is competing with food-producing area. And so these are some of the green polymers that we all know and love. And of course, the other issue is with that scale of materials, you say, oh, well, it's biodegradable. What are they degrading into? We're talking about billions of tons of degradation products. It's not a trivial problem. On the other hand, here, we need ethylene or propylene, and the Leviathan will provide all the ethylene and propylene that Israel will need for 100 years. And in fact, so in terms of life cycle environmental impact, these look very good. In terms of green principles, they're not bad either, and they beat a lot of the bio-derived polymers. It's either the Sierra Club or Greenpeace has looked at all the polymers that we could use and basically has concluded if you have to use a polymer, the polyolefins are as good as any others. The only issue they have is they don't degrade, so we ought to be recycling them. In Indonesia, apparently all of the polymer garbage is just thrown into the ocean. And so we need to learn how to recycle something that in fact is that durable. So that's just sort of a FYI part of the lecture. Now let's look at some chemistry, catalytic chemistry. So we needed to develop chemistry which would simulate the alumina surface. And so we chose this. We needed a Lewis acid which is really durable, Teflon coated, has no fluorides that are easily abstracted or any anions, and we chose this perfluoroborane, which had actually been made by Gordon Stone. You reacted with any of these molecules, and immediately you can see in the NMR, one of the methyl groups now has the coupling to the quadrupolar borane. This chemical shift goes way downfield. You add ethylene and it polymerizes ethylene like crazy. But the really important thing from fundamental science is now we can do X-ray diffraction, we can do calorimetry, we can actually measure the enthalpies of these reactions. We can do all sorts of solution phase and solid state NMR. And these are two of the crystal structures. And it gives you a picture of the stereochemistry. So what has happened here is a methyl group, as we proposed, has been abstracted from the metal center. This is one that has a metallocene, 2 cyclopentadienyl rings, and the methyl group here, I'm going to rotate these in a minute, but the methyl group here is this methyl group. So what happens is there's a series of olefin insertions, very, very rapid, very exothermic, and there's always a competing reaction. It's called chain transfer. And every so often, rather than propagating by insertion, there'll be an elimination reaction to produce a polymer chain with an olefinic end group, and then a new growth will begin. This is one that was made famous by Dow Chemical. So there's a cyclopentadienyl ring, a silo bridge, and an amide group. And let me rotate these just so you can get some appreciation of the stereochemistry. And the only downside of this is I find it begins to hypnotize the audience. But now you can see here's the perfluorophenylborane, here's the methyl group, and this interaction is largely electrostatic. It's not an agnostic interaction. Here's the methyl group here where the olefin will insert, and it turns out you can vary the structures and the stereochemistry such that I can feed it propylene and get isotactic polypropylene or syndiotactic, so it's very, very well defined. And let's look at the constrained geometry catalyst now. And you can see this catalyst is much more open, much sterically, much more expansive. And so right after we discovered these, we decided, for a variety of reasons, to partner with Dow Chemical to see just how far this chemistry could be taken. So we've rotated this enough, right? Everybody got a picture of the stereochemistry. So we partnered with Dow, and through 2015, this chemistry has produced about 30 billion kilograms of high-performance polyolefins. That's about $100 billion in sales. And what's so important is we don't want to just make straight chains. We want to be able to introduce structures like this. And how do you do that? And now we're going to talk about the finesses of changing from a linear polymer to other structures. And let's start by asking the question that I mentioned already. Lots of metalloenzymes, exquisite examples that Mother Nature uses, use 2 proximate catalytic centers. One may bind the substrate in one way or activate it in one way, and the other may, for example, take water and make it a very powerful nucleophile. So let's start with a relatively first-gen example here. We're going to take a titanium and a zirconium and combine them in this kind of linked structure here. And what we know about titanium is it is a very active polymerization catalyst, produces very high molecular weight polyolefins. It ravenously grabs onto any comonomers. So we've shown ethylene, but obviously it could be hexene, propylene, et cetera, et cetera, et cetera. More in a minute. The zirconium, on the other hand, for interesting reasons, tends to make oligomers. So relatively short chains, maybe 50 ethylenes, maybe 75, and then the chain transfer process limits the growth and it makes another chain. So I've abbreviated it this way. So you run this polymerization under very, very carefully controlled conditions, and you never see any of the oligomer. You never see by GC, by NMR, by anything. The reason is within this coordination sphere, it's captured by the titanium, so it can enchain ethylene, it can enchain the oligomer, and you make some very unusual polymers now that look like this. It's very hard to imagine another easy way to do that, starting from only ethylene. And I'll simply say we've characterized these polymers with just about any way you can imagine. And so this is interesting, but you might say, you know, looking at the periodic table, well, titanium, zirconium's right under titanium. What's the big deal? That's not a stretch of the imagination. So what would happen if we used another metal in combination with titanium that even proceeds by a completely different polymerization mechanism? What might we see? And so we're going to look at this system. Here's the titanium again, very good polymerizer of olefins to make high molecular weight polymer. And this chromium compound, originally developed at BP actually, makes 1-hexene. It trimerizes ethylene to make 1-hexene. And the question is, if we made, so this is called a tandem catalyst. What would happen if we could link them together in a binuclear structure where, in fact, we could even vary the proximity of the two centers? What might we see? And it turns out, as an aside, industrially, they copolymerize ethylene and 1-hexene, for example. You have to make the 1-hexene separately. It's expensive. Anytime in the chemical industry you have to do another step, it costs you money, time. What if we could do it all with this one catalyst? So I'm not going to go into the synthesis. This was done by a really talented young chemist named Shan-Fu Liu. But he made a series of these where n is varied from 0 to 2 to 6. And of course, the control is the tandem where they're not connected at all. The first thing to look at, which is really instructive, is the carbon NMR of the polymeric product. And here's what we're looking for. This is, if we insert 1-hexene in the polymerization, we'll get N-butyl branches. And BR, stands for branch point here. So we're going to look at the C13 NMR. And here's the tandem, and maybe there are little blips that show you're getting some copolymer. Here's N equals 6. Here's N equals 2. And at N equals 0, there's a very large prominence of N-butyl branches. And this sort of bar graph sort of summarizes the same thing. The activity is lower for the multinuclear catalysts. The molecular weight is a little bit higher, but we see this very striking behavior. So now a kineticist would say, well, what about the temporal characteristics of the selectivity you're seeing? So here's the tandem. Remember, as the catalyst is turning over, one part of the tandem is making 1-hexene. That's a little machine to make 1-hexene. Another is making polymer. And this is branching in the product per 1,000 carbons. And what's amazing, for the tandem, it goes up because that little 1-hexene machine is filling up the reaction solution with more and more 1-hexene. But in the binuclear catalyst, the conversion, this is time, so it's conversion to a chemical engineer, is barely changing. And this is another way of, this is graphing the amount of oligomer you can get, and you see the bimetallic is operating differently. And what do we mean by operating differently? This is just to show you, it's an FYI, you might say, well, what do the N groups look like? And so for the tandem here, it's a mess. There are all kinds of N groups. On the other hand, for the binuclear, it's very, very clean. And there's one other thing we learned. So the tandem has internal and vinylic olefins. It's not a well-controlled process. Here's the bimetallic, and it's almost all these terminal vinyl groups. And one other thing, for the polymer aficionado, the molecular weight is independent of the ethylene concentration. And that means that the mechanism is not a standard beta hydride elimination, but it's what's called chain transfer to monomer. Let's put this all together. I know this is complicated, but let me show you our picture of what's going on here. And let me start by how this catalyst, if you had a mononuclear chromium, it would make one hexene. It would produce it by a redox cycling, reductive coupling of ethylene to make a metallocyclopentane, add one olefin to make a metallocycloheptane, and then reductive elimination and beta hydride elimination, reductive elimination to spit out one hexene, and then the cycle would continue. But when I add the titanium here, something really different happens. And what happens is, and in terms of the sequence, it's hard to say, does the titanium assist the collapse of this metallocycle? But the DFT calculations show species either like this or with the connectivity reverse. So there's an agostic interaction, a weak CH interaction with the electrophile and a pi bonded olefin. And what would happen then, what happens, we propose, is enchainment. So the one hexene inserts into the titanium carbon bond. Meanwhile, the chromium is making a new equivalent of one hexene, but this species can also react with ethylene. And the net result is then we get a polyolefin with N-butyl branches. Remember, the one hexene is enchained to give butyl groups. We see those in the NMR. So this is, remember, the one hexene maker. This is the polymer maker. Now, there's an interesting question here. So I met the board of governors of the Technion. Northwestern has a similar board of trustees. How do you explain the question here of what happens? How tight is the control by which this one hexene is enchained into the metal, into this catalytic assembly? So for our trustees, remember Northwestern is a member of the Big Ten Football Alliance. You say the center hikes the football to the quarterback tosses it over to another player, and how often does that other player drop the ball? And so all of a sudden they get it. They say, oh, now I understand what you're talking about, Professor Marks. So how tight is this control? How could we test that? So the way to test it is we're going to add one pentene externally. And the question is whether an external olefin can compete with this olefin that we've made intramolecularly and under this very tight chemoselective control here. And the one pentene, so if one hexene gave us butyl branches, if the one pentene is enchaining, we'll get propyl branches. And so let's do the NMR experiment. And always our control is the tandem catalyst. And so we're feeding a 10th molar 1-pentene. We've put in a lot of 1-pentene. And you can see propyl branches mean that we've enchained a lot of 1-pentene versus butyl branches. So this is the tandem intermolecular. 91% of the branches are N-propyl when we add 10th molar pentene. On the other hand, now let's look at our tandem binuclear catalyst. Only 5% are N-propyl. 94.5% are N-butyl. So what it says is that normally that player over there catches the ball. He or she doesn't drop it. And so if I'll skip this. This is more detailed than you need. What it says here in terms of how intact is the transfer, it's good. It's not 100%. It's about, what did I say, 98%. But if you sort of think of this as the way an enzymologist would think of it, that means that the effective local concentration of one hexene to so outcompete the one pentene is about 10 molar. So that's pretty good. It's not perfect, but it's pretty good. Now I want to come back. I love symmetry. I want to come back to where we started with me getting almost thrown off the podium at a New York ACS meeting because people didn't believe something like this. So now let's explore these ideas a little bit more to bring full circle to the discussion. But remember, we proposed something like this. It's a hot catalyst. Now, one of the things I did learn from my heterogeneous catalytic colleagues, it's a really nasty question to ask heterogeneous catalytic people. What percentage of your sites are really catalytically active? What percentage are actually doing something, and what percentage are just spectators? And you can probe this in two different ways. We could see by NMR when we fed this ethylene, only a small percentage of the sites reacted with ethylene. Or you can run the catalytic, let it turn over and titrate in a poison, which kills the catalyst. And either way, you can see only about 5% of the sites actually do any catalysis. And that's really surprising. And if you were an industrial manager, it means 95% of the catalysts you're buying are just being thrown away. So then you say, well, what's going on here? Somebody said, oh, you dummy, you shouldn't have used alumina, you should use silica. So silica is a weak Bronsted acid. So that means the conjugate base is a strong base. And in fact, this one is completely dead. And you can see in the NMR all the hallmarks of something that looks like an alkoxide rather than this 14-electron cation. So then you say, well, what would happen if instead of a weak Bronsted acid, which has a strong conjugate base partner, I use a really, really strong Bronsted acid? What might I see then? And some of the students in the group said, you know, I know the boss comes up with crazy ideas, but this is the craziest yet. But I convinced somebody to try it. And what we're going to look at are sulfated metal oxides. And they're extremely powerful. Some people say super acidic Bronsted acids, and some reviewers say there's no such thing as a super acidic Bronsted acid. So somewhere in between. They probably have structures like this. Joachim Sauer at in Berlin has done really detailed quantum chemical calculations. Avelino Kurma was the guy who really sort of pioneered the catalytic chemistry. Most of the catalytic chemistry is hydrocarbon chemistry because these catalysts chew on saturated hydrocarbons and attack them. Joachim Sauer, some of you may know, is Angela Merkel's husband, the Chancellor of Germany. So may help his funding, I don't know. But in any case, we decided he's a very nice and very smart guy. So we decided to try some. The first experiments, we took this zirconium compound. We wanted one ring for a variety of steric reasons. You put it on sulfated alumina, and the first thing you see, and these sulfated oxides are trivial to make. You cook the metal oxide up with sulfuric acid, and then you calcine it under oxygen. So in comparison to making all these exotic perfluoroaryloboranes, you know, you can make a bucket of this. And what we see is the OH groups in the IR go way down when we put the metal complex on it, and the NMR looks like this. You feed it ethylene, and it polymerizes ethylene like crazy, and you do the poisoning. I think I have a poisoning plot on the next slide. We'll see. You conclude that not 5% now, but almost 90% are catalytically active. And then you feed it benzene and hydrogen. And of course, you know, a classic catalytic chemist would say, oh, you need rhodium on titanium, platinum on silica if you're going to hydrogenate, or palladium on charcoal to hydrogenate an arene. And it hydrogenates benzene like crazy. The very first experiments done here, Morse Eisen is out of town. Actually, Morse did, not with zirconium, but he did a thorium compound in my group. 97% of the sites are catalytically active. Now, the first ramification is, for the first time now, what you see spectroscopically is going to be the real catalyst. And we'll get to that in a minute. This compound on sulfated zirconia is, as near as we can tell from the literature, the most active benzene hydrogenation catalyst that's ever been found. You might say, so big deal, you're hydrogenated benzene. We'll come to that because there's some really interesting implications. The kinetics are 0 order in benzene, 1st order in hydrogen. And what that says is this benzene binding is rapid and irreversible, and the turnover limiting step is the first hydrogen addition. And we'll say more about that in just a minute. But now, with a system like this, for example, we can bring on the whole armamentarium of physical methods without worrying that we're looking at a spectator. We're looking at, instead, the real catalyst. Oh, this is just a poisoning experiment. So this is the turnover frequency. This is benzene hydrogenation. It's done in a slurry, extremely rapid stirring, and we titrate in little bits of either water soluble in benzene, or neopentanol, or we've used sterically hindered phenols, and what you see is a response like that. And what it says is what's happening each time you drop in some of the poison, you've knocked out a certain population of the catalytic centers, and that the slope is linear suggests they're all responding approximately the same, and the intercept is near 97%. So virtually all the organozirconium sites are catalytically active. The other thing I should mention is the great advances in NMR since the early CPMAS work we did. So this is work, some of it's done with Merrick Pusky at the Department of Energy Ames lab, but essentially now any kind of 2D experiment that you would do in a solution NMR experiment to solve the structure of an analyte, you can do on the surface. And this is just showing all the kinds of experiments you can do to show that you've made something like this. You can also do, let's do a little more solid state NMR just to show you the kind of finesse. So this is the zirconium compound. The methyl groups here are C13 labeled. And so this is the zirconium methyl signal. It's a C13 experiment. There's a little bit of, now this is really peculiar. You might say, well, wait a minute. This looks like the methyl that was transferred to the surface, just like in that first experiment I showed at the beginning of the lecture. And you say, we got this sulfated, oh wait, this is sulfated alumina. Okay, so there's a little bit of transfer to the surface. C12 analog of the zirconium compound, and now you don't see this. You don't see this. You just see the ring signals and the very weak methyl signals here. Now we're going to take C13 enriched benzene and put it on the surface. And here's the signal of, it's probably chemisorbed on the surface, maybe interacting more strongly than this. Now we're going to take the C12 methyl compound and add benzene to it. And now you see a benzene signal, but it is shifted from here. In fact, it looks sort of like the position that some D0 benzene complexes that are in the literature have been reported at. And now we add hydrogen, and all we see, the benzene signal is gone. All we see is cyclohexane. So in situ, this shows what's going on, but this is a question, and let's go on to the next step. So now we have a structure on the surface that's 97% approximately of these species are real catalysts. We can do XAFs. This we've done with Jeff Miller, so the zirconium XAFs. And we can do DFT calculations, starting with Sauer's picture of the sulfated oxide surface, and then seeing how organometallic molecules interact. Let's start with the XAFs, and this is Jeff Miller, and Jeff is a very clever guy. So he said, give me some of this, and give me some of this, and we'll do the zirconium XAF, and we'll subtract one set of data from the other. And so you can find the zirconium methyl distance, and this is the literature single crystal structure. This is what we get by XAFs. Same for the ring carbon distances. So the picture then, the DFT is with Alessandro Motta at the University of Rome. Combine the XAFs and the DFT, and you get a picture of what's happening. And what's happening The first big surprise is the zirconium-oxygen distances are very long. So in a typical covalent zirconium alkoxide, they're going to be 1.95, something like that, 2.36. So it's as if this D0 14 electron cation is floating on an anionic oxide surface. I can't tell you about the mobility. We should measure that, try to measure that by NMR, but it's as if it's floating. It's a very weakly bound cation, which explains why it's so phenomenally reactive. Now, I want to go one step beyond this. Oh, this is just an aside. It just came out in ACS Catalysis. This is the Hafnium Analog. It's reactive as hell. The starting material was made at Dow, and that's now commercialized. They're looking for catalysts which will run at 180 degrees C. And this hafnium compound does, and it has a whole interesting surface chemistry. Read all about it. Let's come back to our zirconium compound, which we talked about, and we're going to hit it with benzene. And Jeff Miller emails me, there seem to be 6 carbons now, an additional 6 carbons sitting next to the zirconium. And 100% of the zirconium sites reacted. And so this is the picture then of the sort of, if you like, the resting state of the complex. So one of the things that it sort of asks is, in coordination chemistry, dating back to the days of Alfred Werner, people were looking for the ultimate non-coordinating anion, or weakly coordinating. Maybe something like this is just what, I don't want to say just what the doctor ordered, just what the professor ordered, whatever. So this is a picture. It's a complicated DFT. Alessandro worked this out of the steps. But basically, and some of this goes back to work that Morse did with thorium, but basically the picture is that it looks like all the hydrogens are delivered to one face of the arene. Once it's caught, it's probably caught as something like this. So this is really crazy. If your elementary organic class, you gave them a metal hydride on an exam and benzene, and they wrote that the metal hydride inserted into the benzene carbon-carbon double bond, that's 10%, 10 points off automatically, right? That's crazy. But this is in fact what happens, and you can see argue from bonding energetics, it's exothermic, but also there's stabilization here. And the minute this event occurs, then this bond is cleaved, and it's basically this sequence again and again, and you can work through using different kinds of arguments. This energy span analysis that Sasong Sheikh developed, that in fact the turnover limiting step is in an excellent agreement with the kinetics. It's 0 order in benzene, 1st order in hydrogen. But let's come back to this really interesting question. What else can you do with this catalyst? So if you feed it benzene and toluene, Mady Stalzer found that it had large selectivity for benzene. You feed it benzene and ethylbenzene, large selectivity for benzene. Benzene and mesitylene, very large selectivity for benzene. So you say, well, that's sort of academically interesting. What's in the gasoline we burn? It's about 35% aromatics. Benzene is a carcinogen. It has to come out. How to get it out is something that's really puzzling people. Maybe catalysts like this are just the way to detoxify benzene. The other thing I mentioned very briefly, but just a little more detail, you see, if you use, for example, deuterobenzene, you can see from the NMR that the H2 is delivered in pairs all to the same face of the benzene ring. So you say, well, that's sort of interesting, but is it some kind of a fluke? So Mady started looking at other arenes. So xylenes, meta, ortho, meta, and para. And she said, something must be wrong with the GC. I only see one peak. And then she did palladium on charcoal, and then you don't see one peak. And so the conclusion here is that you're making unusual cyclohexanes. How general is it? It's really quite general. So then you say, okay, well, that's sort of academically interesting, but you know, in the last decade, there is so much beautiful work selectively activating saturated hydrocarbons. So Melanie Sanford, many other groups in the US and Europe, and this is just something we pulled from the literature. So you can start with this cyclohexane here, stereopure, and you can do all of these catalytic transformations. And so the interesting prospect here, a lot of these compounds have never been made. They've never been made. This catalyst will not do well if the substituents are extremely polar, like a carboxylic acid, but lots of others that can be protected, it's really quite good on. So this is a question. What can you do with a catalyst like this? And we think there's some really interesting prospects. Okay, in the last 10 minutes, and then you can finish whatever food is left there, I want to talk about these dioxo compounds. And the motivation is lots of molybdenum, and again we're talking about cheap metals, just like zirconium. Molybdenum oxides are very cheap, and for example, there's a lot of catalytic chemistry to chew on biofeedstocks, oxidation, olefin metathesis. A lot of these are just as sort of black boxy as where the zirconium chemistry started 20 years ago. And the typical way that these catalysts are made is called wet impregnation, which means you take this molybdenum compound, you dissolve it in water, you stir it with some support, and you heat the hell out of it. And it's always drawn this way, but in reality, the more and more people look, there are all sorts of oligomeric species, crystalline species. So what we wondered is, could we use a molecular precursor just the way we did with the group 4 organometallics and really try to dial in and make species like this? And for a variety of reasons, including it's sort of a hot area in heterogeneous catalysis, we decided to use activated carbon. And the state of the art, like the zirconium chemistry, has advanced enormously from the days when people would just dispense your work as support effect. So you can do temperature programmed desorption to probe the acidic sites on the carbon, and then on the molybdenum complex on the carbon, X-ray photoelectron spectroscopy. You can look at the molybdenum by itself. You want to look at the carbon to make sure that there are no other species that would cause a problem. Oxygen can tell you a lot about the nuclearity of the metal oxides, and of course X-ray diffraction. Temperature programmed hydrogenation, you basically pass hydrogen over it, ramp the temperature, and then look for where it exotherms. No one has ever made a molybdenum complex, oxo complex, on any support that exothermed at such a low temperature, and it looks like it's approximately 50% of the molybdenum sites. What you can't do is take an IR, because molybdenum, this carbon is black. You can do UV Raman, it looks like you see, I mean, any of the molecular people would say, oh, well, you want to look at the molybdenum oxygen stretching frequencies, symmetrically, asymmetrically coupled. You can get the angle, you can get information on the oxidation state. We're not there yet, but we know a lot about the acidity, and here's XAFs, and with Jeff Miller including Zanes, so looking at the edge, everything says pretty much it stays as molybdenum 6, but probably when we add the hydrogen, we lose some of these short molybdenum oxygen distances. We probably get something like this. Now, so you might say, well, what is the motivation for studying this stuff? And that starts on the next slide, and I only have time to talk about 2 of the reactions that this catalyst does. I'm going to talk about transesterification first, and the idea is catalysts which you could use to treat biomass, and then next we're going that's here, and then we're going to talk about something that's a real surprise. So, and most of this work was done by Tracy Lohr, absolutely phenomenal postdoc from Canada. And these catalysts are really, really active. This molybdenum oxide on activated carbon, and we look for leaching. We make sure that the filtrate is not catalytically active. We do all of those kinds of things. But it's really, really good to do transesterification, and you can just filter this off at the end of the reaction. You can reuse it again and again and again. You can use it under air, no degradation. You can even use, say, triglycerides, which are vegetable oil type things, to make glycerol and esters. And the mechanism, which has some homogeneous precedent, is addition of alcohol. So these oxo groups are not innocent ligands to make a hydroxy alkoxide, nucleophilic attack, transesterification, and then you make this alkoxide, which alkoxylates with ethanol, and you're back where you started. Well-behaved kinetics. It's first order molybdenum, first order in ethanol. This is in massive excesses of ester, reasonable I-ring analysis. But let me look at the last reaction, because that I think is the most surprising one. So there are a number of very, very good groups in Asia, in Europe, in the US, in Israel, who have been looking at the following reaction. It's a desire to make hydrogen from what's called bioalcohols, so that are derived from fermentation. And you can do it with all of these catalysts, very elegant work, but you always make an equivalent of carbon dioxide, and that's bad. And sort of an interesting question that's been in our mind, so if the sequence is something like you lose hydrogen to make formaldehyde, and then you go on and you end up finally with CO2, could you stop here? With the right catalyst, none of these catalysts will stop there. They always make carbonates or species like that. And this is Tracy's work. And the idea is, and it works. It works with bioalcohols, and that means aqueous solutions of alcohols, to give, say, formaldehyde. And these are low boiling species, so you see some in the mass spec, you see some oligomers. So this is an example of some mass spectrometry. Here's hydrogen evolution, formaldehyde evolution. 1/3 of all the methanol made in the world is used to make formaldehyde for all kinds of plastics, things like that. So it's a commodity chemical. We cannot find any CO2 or any CO in these reactions. Negligible molybdenum leaching. We've done every kind of isotopic, we meaning Tracy, every isotopic labeling experiment you could think of. And the thermodynamics in fact, it looks a lot like the Milstein chemistry, where you take alcohol and amines and you make amides or esters, and it's driven partly by hydrogen being evolved. There's a little bit of that here, and also you form oligomers of the aldehydes, which help drive the reaction. And just a little more detail. So she's done all sorts of volumetric experiments. Here's one where we give it a shot of alcohol, and you can see hydrogen evolved at each shot, and it just keeps going on and on and on. We've done multiple cycles. The mass spec, you can see the aldehyde. This is acetaldehyde. You can see all the oligomers. So it really works, and the numbers are impressive. So even in aqueous alcohol solutions, the turnover frequencies, and these are, I think, 90C, are really quite high. Mechanism: addition of ethanol to make a hydroxy alkoxide. Beta hydride elimination gives you acetaldehyde. These hydroxy hydrides have been proposed in solution work that people have done, and that would eliminate hydrogen, and the cycle continues. And so I think part of the message is these weird supports, these non-classical supports. So activated carbon has carboxylic acid groups on it, hydroxyl groups. Those seem to be the key thing. We've got a ways to go to be where we finally ended up with the zirconium. This is just showing just quickly. So this is using carbon nanotubes and absorbing this. And what we see, so this is high angle annular dark field microscopy, you can see what look like individual molybdenum sites here. And this is also catalytically active. And we're looking at graphene. And this is looking at putting this on alumina, titania, and carbon nanotubes. And this is by HADF, the size of the domains we see. So it looks like on some of these supports, it's predominantly single site, single atom catalysts. There's certainly no evidence for any huge nanoparticles. There may be some clustering as well. This is work that's hot off the presses. Okay, so some conclusions to wrap up. These catalysts are really, think of them, these supports as ligands, as activators. They really change the chemistry in interesting and unexpected and presumably useful ways, including giving us hints about homogeneous catalysis. Ion pairing is very important in the group 4 catalysts. Sulfated oxide surfaces maybe are the ultimate non-coordinating anions. It looks like these oxo group 6 species are going to have a very rich chemistry, especially on non-classical supports. This is really important. The advances since we started in the last 10, 15 years in terms of physical techniques, not only that they exist, but the availability, whether it be XAFs or all the computational techniques, made it very, very productive. And there's lots left to be learned. So I don't want you to think I did this work by myself. Where's Northwestern University? People may wonder. It's not in Seattle or Portland, Oregon. It's on Lake Michigan. We're the first suburb north of the city of Chicago, which is a very ethnically rich international city, good airports. It's on Lake Michigan. The water is very clean. We have boating and swimming. Here's a beach. You can learn how to sail a sailboat. Very nice environment. The lake is about 100 miles across here. The world's largest supply of fresh water. These are within the last decade, the graduate students, postdocs, and collaborators internationally that have worked with us. Here's the source of support. And so my group is divided into 4 teams. And we used to work mainly on actinides in the organometallic group. It became known as the A-Team. Do you remember the old TV series, the A-Team? Yeah. So I was Mr. T and part of that. I don't know how that idea came. So these are the people in the A-Team who did the work I told you about. Here's our entire team here. And so with this, I want to thank the Technion. I was saying to somebody the very first time I was here, it was 1986. And I know that some of the students were not born then, but it has changed tremendously. I think I said it at my speech yesterday that in 1986, when you talked about the startup, it didn't mean a startup company. It meant whether your old car started up that day. So things have changed tremendously, but the hospitality has remained constant. So thank you very much for the invitation.